Hey, AP Pre-Calc, it's Miss Adams. This is Day 2, Lesson 15, Chapter 2, the very end of our chapter. Let's read this top paragraph. It's important to understand. In the first lesson on semi-log plots, we knew the base of the exponential function. But what if we have real-world data and don't know the function and we don't know the base? We could take the logarithm of the y values and then we could graph using a logarithmically scaled vertical axis. So whether we have the exponential function of raw data, in either case, we want to linearize the data by transforming the y values to a log scale. This is the big idea of semi-log plots. For example 7, we have the table gives the value for a function for selected values of t, which really should say x. That's not a t in our table. And we want to graph the data on the semi-log plot, label the axis, and decide what does the graph say about the data. Then we want to approximate the values for f of 3 and f of 9 just by using the graph. So on our table here, 0 and 3/10, that's going to be 0 and 3/10. I can't graph. Let's see, we can graph 2 and 1.2. We can graph 4 and 5.8. 5.8. 6 is 28, or 5 is 12.6, so 10, 12.6. 6 is 28.8, so really close to 30. 7 is 65 and 4/10, so 60 is here, 65 and 4/10. 8 is 156.2. 10 is 820. So 800 is way up here, 820.3. We can't graph past that. Oh yeah, I can. 12 is 4,000. Let's see, we got a mess there. What was 8? 100. Oh, I'm off here. 8 is 156. This one's out of place. 10 is 800. So 823. 12 is 4,000. So 12 is 4,300. And then 13 is 9,900. So what do we see there? Looks like we have a straight line. So data is exponential because the graph appears linear on a semi-log plot. Let's go back and answer that question. The data needs to be exponential. Since the graph is linear on the semi-log paper. And if we want to evaluate or estimate the f of 3 and the f of 9, looking back at our picture here, I'm going to change colors. The f of 3 looks really close to maybe 2.8 or 2.9, and the f of 9 looks like it's about 350, I guess. So f of 2 is really close to 2.8 or 2.9, and f of 9 is about 350. They've also asked us to label the axis. So this is f of x here, and this is x here. And in red, we had f of 3 here and f of 9 up here. On example 8, we want to graph the data on the log paper. When x is 7, y is 3. So 7 is going to be in here. Y is 3, right about there. When x is 12, y is 16, so 10, a little bit more than half. When x is 20, y is 39, so 10, 20, 30, so this is 40, right about there. When x is 31, y is 53, so right about there. And when x is 42, so 42, y is 88, so this is 100, 90, 42, 88. And then when x is 54, y is 125, or 125, somewhere in there. So it appears like we've got maybe some logarithmic graph here. And since the plot appears logarithmic, the data is most likely linear. In example 9, they are telling us the function g is graphed on the semi-log plot where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for g of t? So if we use those ideas from last time, the log of g is b plus mt. So g of t is 10 raised to the b plus mt power. If we have 10 to the b times 10 to the mt power, we could have, let's see, we got what, 0, 2, and we got 1, 10. It looks like the average rate of change is the log of 5, and the b value is 2. So our b value is 2, and we've got 5 to the t power. That seems like C would be a good graph, a good equation for that graph. Moving on to example 10, the graph below is data collected from a bacteria growth bee in a culture that was recorded over a period of 3 weeks. The semi-log plot shows the number of bacteria present beginning on day 3 through day 21, and we want to write the function for b of t. Looking at the values, we could maybe make a little table here. We've got 3 is 150, 6 is 300, 9 looks like 600, and 12 looks like 1200. It looks like we're doubling every 3 days. So this is the time, this is the bacteria. If our rate is doubling every 3 days, and we could say that b of t, let's see, b of t is some number a times base 2 to the t divided by 3 power, and we could use the point, let's use the point 6, 300. So 300 is a to the 2 and 6 over 3 power. 300 is 2 squared, so that's 4a. That gives us a is 75. Therefore, we know a and we know the base. The b of t is 75, that's our initial amount, times base 2 to the t over 3 power. So we used the data in the graph to make a table and solve for the unknowns using that table. Example 11, we want to use the table of values to graph the points on a semi-log plot and decide if the graph indicates exponential model would be appropriate, and then we want to explain why or why not. So graphing 0 and 3/10, that's going to be 1, 2, 3/10 is right here. Whoop. 0 and 3/10. 1 is 6/10. 6/10. 2 is 70. So 10, 20, 30, 40, 50, 60, 70. 3 is 300. 100, 200, 350. And 4 is 800. So the plot on the semi-log plot does not follow a linear pattern. Since this one's kind of out of place, exponential is not appropriate. So we want to make some kind of a statement like that. The points on the semi-log plot do not appear linear. So exponential is not appropriate for this set of data. One more example. Okay, so example 12, our last example, we want to choose an appropriate graph. It appears the table gives selected values for some function called k. We have this table here, and which of the following graphs could possibly represent this data in a semi-log plot if the vertical axis is logarithmically scaled? So the first thing I did was I wanted to figure out what the rate of change was. And that way we could write some equation in the y equals mx plus b format. So taking that into account, we could take the log of 80 minus the log of 52 divided by the change in x, which is 2 minus 1, and that would give us the slope of about 0.18708. Then I would need a b value. So it appears if the function is, we have equally spaced input intervals, and we want to consider what's going on with the output intervals. So in my estimation, using my calculator, I noticed that I was going up by about 1.5, multiplying by 1.5 each time. And I'm really close to that for that ratio. So it appears like the ratio is about 3/2. And if we used that idea in our search for the right equation, it looks like we would have an exponential function. So k of x seems like it's exponential. And on an exponential data set, we would look for a linear equation. So this one, graph A, does not look linear. Graph B, I don't know, it could have a slight curve to it. Graph C and graph D appear to be more in line with linear. Get a ruler out here. Maybe have a straight line. So graph I'm leaning toward graph C right now. Let's see, graph D. And we want to compare these to the table. So you got a slight slope. Whoop. The next thing I'd want to do is try to figure out what our B value would be. So we don't know the B value. And one way to do that, if we know the data in our table is exponential, we could say y is a to the b x power. And then I could use maybe the 0.280 and say 80 is a to the 3 over 2 squared power, which gives us 9/4. So 80 times 4/9 would be the a value, and that a value is about 35.5. So this one is not 35.5. This one, 10, 20, yep, this one is close to 35. So I'm thinking choice C is our choice for the data set. We could have a y equals mx plus b, because b is really close to 36. And it appears like that would be our data set. When x is 1, y is 52. See, when x is 1, y is not 52 over here. So that, my friends, is the end of Unit 2 for AP Pre-Calc. Hope you do well on your review and your test, and I'll see you around for Unit 3.